Hi everyone, so I kind of just wanted to go over the difference and try to figure out what force am I looking at when I am looking at particles, because it can be very discouraging and also frustrating trying to figure what force is what given the information. So when we are looking at compounds, we need to look at whether it's ionic or covalent. So remember, ionic is between a metal and non-metal, and that's when you're transferring electrons, and then covalent is between a non-metal and a non-metal, and you're sharing the electrons. So there are different types of chemical bonds. We either have ionic bonds, we either have non-polar covalent bonds, or polar covalent bonds. When we are looking at ionic, that's when you're having your electrons that are completely transferring from one to the other. We have non-polar covalent, and that's when you're equally sharing amongst the two electrons in order to be stable. And then we have polar covalent, and that's when we have unequal sharing. So that's when we have our dipoles being shown, whether it is partially charged, partially positive, or partially negative. And you can see some examples on the left here of our polar covalent because it has the dipoles. So when we look at polar covalent bonds and they form other polar covalent bonds, the reasoning for this is their shape. And you looked at VSEPR the other day and how they form certain shapes. So when they have a dipole, then this affects the shape overall of the bond. So when we look at a linear structure of CO2, this allows the dipoles to cancel out one another, and so therefore they become nonpolar. But when we look at water, it actually has a bend shape. And so that means that the dipoles can't cancel each other out. And so therefore it does have a dipole and it is a polar molecule. So when we're looking at molecular compounds, these have very, very weak intermolecular forces. So that's, remember, the forces between the molecules, even though they have a strong intramolecular bond, okay? And that's bonds between the molecules. And because of that, they have a very, very low melting and boiling point because they have weak forces, and because of that, they can be easily broken. So that low melting and boiling point means that the forces between them can be easily broken. When we look at bond polarity of our covalent bonds, that means the molecules then increase and the intermolecular forces also become now stronger. So if they have a higher intermolecular bond between them, then that means the higher the melting point. So this is just saying that if we have a weak bond, then it's a low melting and boiling point. If it's a stronger bond, then it's a higher melting and boiling point. So if we look between H2O, it's going to have a very strong boiling and melting point because we have many different bonds we need to break. But if we look at N2, it's very weak, so it's easily broken. So when we look at inter and intra, so make sure you know the difference. Remember, inter, that is when we're looking at bonds, for example, between the hydrogen bonds. If we look at intra, that is our covalent bonds between that molecule itself. So when we look at ionic compounds, there are no intermolecular forces since these substances only contain ionic bonds. So when we look at ionic compounds, they have a lattice structure that requires a high amount of energy to break these bonds, and that's why the intermolecular force is also known as the electrostatic attraction, and you learned about that in a previous video. And all ionic compounds will have an electrostatic attraction. So because of that, they're going to have a very high melting and boiling points. Okay, so all attractions between the oppositely charged ions are going to form electrostatic attractions from ionic bonds. So whenever we look at ionic bonds, they're going to have an electrostatic attraction. So this electrostatic attraction, remember, it's in intramolecular bonds. And when we look at an electrostatic attraction, that's between our positive, negative forces. They're creating a very, very strong bond. So when we look at the ions, they're attracted to one another in an opposite charge. So their adjacent charges are going to be attracted to one another. And you saw this video explanation before with our sodium and our chlorine. They're going to have a bond oppositely attracting to one another, so they might pull a little bit more towards one another. When we look at intermolecular forces, once again, that's between the molecules, and they're not as strong as our intra. So when we're looking at them, we have to look also at their physical properties, so their melting and boiling points, their vapor pressures, and their viscosities. So when we're looking at intermolecular forces, they're strong enough to control those properties. And on top of that, they're also, if you ever hear intermolecular forces, you can also might hear that as van der Waals forces. So they go hand in hand. You might also hear the electrostatic attractions, the same thing. So our intermolecular forces, also known as van der Waals forces, there are 4 different types. We have hydrogen, we have ion dipole, we have dipole-dipole, and we have London dispersion forces. These are the only 4, I don't know why there's a number skip there, but it's fine. These are the only 4 types of intermolecular forces. So the difference between these, though, is that are they going to be between a polar molecule or a non-polar molecule? If we look at our dipole-dipole and our hydrogen, those are between polar molecules. If we look at our London dispersion forces, that's between non-polar molecules. So first is our hydrogen bonding. This is our intermolecular attraction between them, and this is only between hydrogen atom and then only these 3 types of electrons. Oops, sorry, go back. There we go. So it's only between these 3 types. So nitrogen, fluorine, and oxygen, that's the only time you'll ever see a hydrogen bond. So for example, if we look at H2O, it has a hydrogen bond, okay, because of the oxygen and the hydrogen bonding together. And once again, this is only in polar molecules. Okay, so you need to determine, is it polar or non-polar? And if it is polar, you're going to have a hydrogen or a dipole-dipole. And once again, hydrogen bonds is only between oxygen, nitrogen, or fluorine electrons. Once again, if you're looking at a molecule, you can have multiple different forces. You can have a hydrogen and a dipole-dipole. Okay, it's okay to have multiple. That just means that it's going to have a higher boiling and melting point. Then we're going to have, we're going to have ion dipole, and this is also inter. And in this situation, this is the attractive force that results from the electrostatic attraction between an ion, okay, so it's an ion, either positive or negative, and a neutral molecule that has a dipole. So we have to look at its bonding with a polar. Once again, it's between polar molecules. But then we have either an anion or a cation that is going to bond with that polar molecule that has dipoles. Okay, so the most common type of ion dipole is between solutions. So we have to look at our solutions. Then we have our dipole-dipole. This is also inter, so this is between our polar molecules. And this is usually represented by an oval shape that has one positively charged end and then a slightly negative charged end because of its dipoles. And you can see the example there on the right. Because we have a polar molecule that is slightly positive end and then the other one's slightly negative, it is known as a dipole because of that pole. When we look at that dipole-dipole, it is causing a much smaller than the forces between, it's called that because of the much smaller forces between the ions. So dipole-dipole force is known as the main attractive force that acts between polar molecules. So it's the most common one, okay? And we look at this as an intermediate strength. So it's not the highest strength, it's not the lowest, but it's an intermediate strength that causes a intermediate boiling and melting points. So it's in the middle. It's not the strongest, but it's not the weakest. Then we have our London dispersion forces, and this is also an intermolecular, but this is between our non-polar covalent bonds. So everything here is between covalent bonds, but now we're looking at non-polar. And so when we look at London dispersion, it is actually the weakest form of force between our bonds. And it is usually very weak for small molecules, but it does strengthen as the size of the molecule increases. So it is the weakest, but it can increase in strength depending on the size. There is a YouTube video if you want me to show you, I would be happy to. It just goes over the London dispersion forces. But the point of this is that it's not a permanent partial charge. So when we look at London dispersion forces, it's about like a temporary partial. So it does have an attractive force, but it does look at the unequal charge between the molecules that we're taking a look at. So we have two examples. We can have an even dispersion of electrons or a temporary uneven dispersion of electrons that causes a temporary traction. Once again, it's not permanent and it's very weak because it can be easily broken. So if we look at water, is not a good example of London dispersion because London dispersion is easily broken. If we look at, I think, let's say carbon and hydrogen bond, that's an easy London dispersion force that needs to be broken apart. So just take in consideration that when we look at London dispersion forces, it's very, very weak and it's only between non-polar molecules. When we're wondering how do we figure out our melting and boiling points, it's important that we're not going to be able to memorize our boiling points. You are going to be given to them. They are found in the textbook. So do look in the textbook. But when we look at melting and boiling points, we're looking at the strength of the force of our ions or molecules, and that's going to be able to determine what is our melting and boiling point. If we have a strong force, then our melting and boiling point will be very high, like a hydrogen bond. If we have a low force of attraction, like London dispersion, then it's going to have a lower melting and boiling point because it's not going to take a lot of energy to break the bond. So we look at non-polar molecules, once again, that's our London dispersion, it's going to have a low melting and boiling. If we look at polar covalent bonds, then it's going to have a intermediate. And if we look at ionic, that's going to have the highest melting and boiling point. So when we look at ionic, we look at the electrostatic attraction, that's going to have the highest. When we look at dipole, and hydrogen, it's going to have intermediate, and we look at London, it's going to have a low. So here are some charts that you could take a look at that has the melting and boiling points. And you can see based off of the categories what's going to have high, intermediate, and low depending on its attraction. Okay. Solubility is important, but we're not going to go too much in it. Just know that solubility is a polar molecule, and it follows the rule of like dissolves like. So when we look at ionic and polar covalent compounds, they are seen as soluble in water. And when we look at non-polar, then that is seen as insoluble in water, so it doesn't dissolve. Electrical conductivity is also important. So when we look at ions, they must be dissolved in order to conduct current electricity. So for example, only ionic compounds are in aqueous or dissolved state can conduct electricity. So we have to look at our ionic compounds, and those are the only ones that can conduct electricity. So here is a chart that kind of summarizes a lot of the information. So what is the state at room temperature, the electronegativity, melting point, based off of whether it's ionic or molecular. So if you want to pause and save this, you're more than welcome to do so. But this is a great chart. Okay, so do take a look at this. This will be very helpful. I hope that was able to clear some information up on how do we figure out what is what.